To train a 3D detector, you would ideally train and test the model on the same data collection platform in the same geographic region and with similar scenes. Here we have a 3D detector trained on Kitty dataset and tested also on the Kitty dataset. It achieves a high average precision of 73.45%. But what if we didn't have labels for the Kitty dataset? We could train a model on the Waymo dataset and test it on the Kitty dataset. However, you can see that the detector doesn't perform as well. There are many false positives and oversized bounding boxes. This difference in performance is due to the domain gap, and this is caused by differences in datasets such as sensor setup, geographic regions, and many others. One of the factors that causes this drop in performance is the difference in LiDAR scan pattern. Here are 4 similar cars at 10 meters of range from 4 datasets. Despite being at the same range, the point cloud density and distribution of points are different. To address this, we propose to train and test a detector on a unified point cloud representation of cars from any dataset. Our novel Viewer-Centered Surface Completion Network, VCN, is able to estimate the pose of cars from any dataset and complete their surfaces. We train VCN on synthetic scenes with realistic positioning and occlusion. Each car model is placed using Waymo labels for positioning, then we raycast from the origin. We simulate realistic LiDAR scan patterns in this dataset to ensure that VCN learns to complete cars with different scan patterns. To complete the surface of cars in the source domain for training, we use the available labels to isolate the car points with bounding boxes. To complete the surface of cars in the target domain for testing, we use the image instance segmentation with dbScan to isolate the car points. We then complete the car with VCN and post-process it to retain only the generated points that are near the original point cloud to reduce the sensitivity of VCN to noise. We place these cars back in the point cloud to get our final augmented point cloud. We train the detector on this augmented point cloud and transform all new point cloud data into this same representation for inference. Training a detector on this unified representation allows it to learn object geometry instead of overfitting on scan patterns. The result is better object dimension estimation, shown in the tighter bounding boxes, and an increase in average precision. Here are further qualitative results on the Waymo to Kitty domain adaptation setting. Here is the new scenes to Kitty domain adaptation setting.